We've talked about how to evaluate learning algorithms, talked about model selection, talked a lot about bias and variance. So how does this help us figure out what are potentially fruitful or potentially not fruitful things to try to do to improve the performance of our learning algorithm? Let's go back to our original motivating example and go figure this out. So here is our earlier example of maybe having fit regularized linear regression and finding that it doesn't work as well as we're hoping. We said that we had this menu of options. So is there some way to figure out which of these might be fruitful options? The first thing on our list was getting more training examples. And what this is good for is this helps to fix high variance. And concretely, if you instead have a high bias problem and don't have any variance problem, then we saw in the previous video that getting more training examples, well, maybe just isn't going to help much at all. So the first option is useful only if you, say, plot the learning curves and figure out that you have at least a bit of a variance, meaning that if the cross-validation error is, quite a bit bigger than your training set error. How about trying a smaller set of features? Well, trying a smaller set of features, that's again something that fixes high variance. And in other words, if you figure out by looking at learning curves or something else that you instead have a high bias problem, then for goodness sakes, don't waste your time trying to carefully select out a smaller set of features to use, because if you have a high bias problem, using fewer features is not going to help. Whereas in contrast, if you look at the learning curves or something else and figure out that you have a high variance problem, then indeed trying to select out a smaller set of features that might indeed be a very good use of your time. How about trying to get additional features? So adding features, usually, not always, but usually we think of this as a solution for fixing high bias problems. So that if you're adding extra features, is usually because your current hypothesis is too simple, and so we want to try to get additional features to make our hypothesis better able to fit the training set. And similarly, adding polynomial features. This is another way of adding features, and so that's another way to try to fix a high bias problem. And if your learning curves show you that you instead have a high variance problem, then again, this is maybe a less good use of your time. And finally, decreasing and increasing lambda. These are quick and easy to try. I guess these are less likely to be a waste of many months of your life, but decreasing lambda, you already know, fixes high bias. In case this isn't clear to you, do encourage you to pause the video and think through this. That convince yourself that decreasing lambda helps fix high bias, whereas increasing lambda fixes high variance. And if you aren't sure why this is the case, do pause the video and make sure you can convince yourself that this is the case, or take a look at the curves that we were plotting at the end of the previous video and try to make sure you understand why these are the case. Finally, let's take everything we've learned and relate it back to neural networks. And here I just want to give some practical advice for how I usually choose the architecture or the connectivity pattern of the neural networks I use. So if you're fitting a neural network, one option would be to fit, say, a pretty small neural network with, relatively few hidden units, maybe just one hidden unit. If you're fitting a neural network, one option would be to fit a relatively small neural network with, say, relatively few, maybe only one hidden layer, and maybe only a relatively few number of hidden units. So a network like this might have relatively few parameters and be more prone to underfitting. The main advantage of these small neural networks is that they're computationally cheaper. An alternative would be to fit a maybe relatively large neural network with either more hidden units, so if there's a lot of hidden units in one layer, or with more hidden layers. And so these neural networks tend to have more parameters and therefore be more prone to overfitting. One disadvantage, often not a major one, but something to think about, is that if you have a large number of neurons in a neural network, then it can be more computationally expensive. Although within reason, this is often, hopefully, not a huge problem. The main potential problem of these much larger neural networks is that they could be more prone to overfitting. And it turns out that if you're applying a neural network, very often using a larger neural network, often it's actually the larger the better, but if it's overfitting, you can then use regularization to address overfitting. And usually using a larger neural network but using regularization to address overfitting, that's often more effective than using a smaller neural network. And the main possible disadvantage is that it can be more computationally expensive. And finally, one of the other decisions is, say, the number of hidden layers you want to have, right? So do you want one hidden layer, or do you want 3 hidden layers as I've shown here, or do you want 2 hidden layers? And usually, as I think I said in the previous video, using a single hidden layer is a reasonable default. But if you want to choose the number of hidden layers, one other thing you can try is find yourself a training, cross-validation, and test set split, and try training neural networks with 1 hidden layer, with 2 hidden layers, with 3 hidden layers, and see which of those neural networks performs best on the cross-validation set. So you take your 3 neural networks with 1, 2, and 3 hidden layers, and compute the cross-validation error at JCV on all of them, and use that to select which of these is, you think, the best neural network. So that's it for bias, variance, and ways like learning curves to try to diagnose these problems, as well as what these things imply for what might be fruitful or not fruitful things to try to improve the performance of a learning algorithm. If you understood the contents of the last few videos, and if you apply them, you'll actually be much more effective already at getting learning algorithms to work on problems than even a large fraction, maybe the majority of practitioners of machine learning here in Silicon Valley today doing these things as their full-time jobs. So I hope that these pieces of advice on bias, variance, learning curves, and diagnostics will help you to much more effectively and powerfully apply learning algorithms and get them to work really well.